Good afternoon, everyone. I'm Seung-Hwan Lim of InssTek. Before I start, I would like to thank ESA for giving me this great opportunity. Today's topic is multi-material manufacturing with the case of rocket nozzle. With technological advances, there's a growing demand to use materials in various shapes and conditions. I would like to talk about the whole process of applying multi-material manufacturing to industrial environment from material research to practical application. Before we get into it, let me introduce our company. InssTek was incorporated in 2001 and specialized in metal 3D printing business using DED method. We are a technology-based company and have our own technologies in various fields from hardware to software, such as power feeding, optic design, and 5-axis cam. We are based on middle area of South Korea with 45 employees. We specialize in manufacturing AM machines and AM service such as printing, cutting, cladding, and repairing. We have many global partners and customers in Europe, America, and Asia. First, I will introduce DED technology and its advantages. DED stands for Direct Energy Deposition and is a 3D printing method that uses an energy source to make a pool of molten metal and put metal material into the pool and solidify. InssTek uses combination of metal powder and laser beam. DED has many advantages differentiated from other methods. I will talk about four main advantages: scalability, add-up, mechanical properties, and multi-material. First one is scalability. Unlike powder bed fusion and binder jet methods, DED method doesn't need a powder layer. It has a movable printing module that supplies material and energy source to target point. Thus, its printing volume can be expanded to comparatively large size. Also, DED methods and robot arms are a good match. Robot arms can control the motion of printing module with high degree of freedom and wide working range. Second advantage is add-up. DED is suitable for various processes such as repairing, remodeling, cutting, and cladding. Third advantage is mechanical properties. Many people have questions about the applicability of 3D printed metal part to real industry. I brought an example for comparison. These are mechanical properties of stainless steel 316L fabricated with various methods. DED cases values are similar or better than those of existing methods, and also they can be improved through subsequent process such as heat treatment. InssTek has a standard process recipes of more than 20 types of alloys in the table. Various metals such as titanium, steel, nickel, copper, and cobalt are available. Last feature is multi-material. Since the process is performed continuously supplying metal powder to the molten pool, if the metal powder is changed during supply, several different materials can be stacked partially in one process. With this feature, multi-materials can be used in various ways such as bonding of dissimilar metals or gradient materials. It is DED method's own advantage that is not available with other AM methods because it is impossible to control the composition of the material in shape of wire or powder layer. In this way, new type of output can be printed that was not possible with the existing process. The sample in this picture is an example of a gradient material. Judging that multi-material will have a lot of influence in future industry, InssTek is developing leading technology in this multi-material DED field. In this chapter, I will introduce the multi-material rocket nozzle produced by combining these technical advantages. InssTek recently succeeded in manufacturing multi-material rocket nozzle. It is a nozzle slot that goes into liquid fuel rocket used in a high-temperature environment near 3000 degrees Celsius. The rocket nozzle used modeling of the size and structure in the actual field given from the customer, and it took only 200 hours to produce the entire shape. This project is an intermediate step in completing the final outcome. Therefore, at this stage, it has been produced with a focus on confirming the feasibility of implementing various technical features. The nozzle was made of multiple materials. Outside was made of Inconel and Diamonic 75 that belongs to nickel-based alloy which are resistant to the hot environment, and iron bronze was used to make inside in order to estimate applicability of copper-based alloy. In the middle part of the nozzle, the possibility of using recycled powder was examined. The Diamonic 75 powder discarded from the previous process was mixed with the new powder and used for the last zone. This rocket nozzle was manufactured using InssTek simultaneous 5-axis cam technology. The cooling channel inside of the nozzle rotates in a spiral form from bottom to top. Next feature is called add-up. DED method has no restriction on what shape it works on. With the advantage of being able to print on an existing part with various shapes, it can proceed printing in various orders rather than just from bottom to top. Judging that the rocket nozzle part can be a great starting point to apply DED to aerospace field, we have been manufactured various nozzles according to our technology development stage. We start from thinner and a simple shape, and then, developing our advanced powder feeding technology, we obtain the ability to handle multi-materials. Based on this, we succeed in producing multi-material rocket nozzle with cooling channel. The next rocket nozzle that we are aiming for is an FGM rocket nozzle that deals with multi-materials more technically. The production is scheduled to be completed in the first half of this year. So, stay tuned for our updates. In this chapter, I would like to introduce the multi-material manufacturing process owned by InssTek. Rocket nozzle described above was produced in a similar process. The entire process can be divided into 4 stages. In the material research stage, we use several powder feeders to change composition and conduct basic tests for various compositions. And then, process optimization is carried out for the materials to be used in actual manufacturing. After that, establish additive strategy about target shape with 5-axis cam and proceed simulation for generated toolpaths. After all the verification process is over, printing is proceed. InssTek conducts material research using DED method. In order to make a specimen in the existing way, the composition of the alloy must be set in advance, and you prepare molten metal according to the composition, cool it, and go through some machining process to making it into a specimen. However, InssTek's new method that uses 3D printing can make the process very short as indicated on the right side, so that you can get the final object in less than an hour. I will explain more about this method. Material research using 3D printing was conducted previously, but they used powders that were premixed according to specific composition in advance. However, InssTek has established a feeding system that can supply up to 6 different powders in situ. Therefore, individual element powders can be supplied changing its amount to make specimens with various compositions at once. This method is also called in situ alloying and has the advantage of being able to quickly perform tests with various compositions. This paper is for evaluation the in situ alloying's effectiveness. In this study, samples made of Inconel alloys were compared with the samples made of in situ alloyed nickel, chrome, molybdenum, niobium, and iron pure element powder which is prepared with the same composition as Inconel alloy. Finally, they found that it shows similar mechanical properties in 2 samples, which means in situ alloying can be a new alloy research method. With the MXLab system, which was developed by InssTek, material research proceeds as follows. Using the software Material Designer, you can choose a shape, size, and composition of the specimen to be tested, and prepare required powders on the 3D printer. Remaining part is waiting until the specimen is printed and analyzing it. It is a very simple process that takes less than an hour. Now, let's experience how to study materials with MXLab through video. The next video is about how to research high entropy alloys. After basic material research and material selection, the next step is process optimization. The quality of the output can be guaranteed only when it is proceeded with stable process parameters. Particularly, in case of multi-materials, various verification procedures are required because the mechanical properties of the mixed part and the individual methods can be different from each other. Therefore, it is recommended to make various specimens and evaluate them. Next, ICAM software will produce a toolpath. Even for the same shape, the quality of the result may vary depending on the printing strategy. InssTek's ICAM produce optimal toolpaths based on know-how accumulated over a long period, and a simulator built in the CAM tests the possibility of collision using the generated toolpath. This video is about how we simulate the toolpath. Now all the preparations are complete. We will watch the Lock and Nozzle production video together. Multi-material manufacturing requires a continuous process from material research to shape production. Based on its own hardware and software core technologies, InssTek launched Machine for Material Research MX Lab and Machine for Manufacturing MX Fab. With InssTek's product lineup, customers can experience serial process from material research to manufacturing. In this chapter, we will look at the possibility of how Ded technology can be used more in space industry in the future. The potential of Ded technology is infinite. I will explain its value by dividing it into a material perspective and a manufacturing perspective. First, Ded technology will contribute a lot to the study of new alloys in the future. As mentioned earlier, in situ alloying is recognized as a new material research methodology, and various research results using this technology are being published. Being able to quickly make and test various compositions of samples will continue to be a good solution for space environment that requires new materials. The second value is the use of multi-materials. It has a tremendous advantage in that it can give the necessary characteristics for each area when manufacturing parts. It is possible to manufacture optimal parts that take into account various factors such as mechanical properties, price, and weight. The third value is the content that encompasses the materials and manufacturing. Materials that are difficult to handle with existing manufacturing methods such as machining can be handled with Ded technology. For example, there is a titanium alloy which is difficult machining. However, if manufactured with Ded method, it is much more efficient that it only needs to be machined in the minimum area. Next project is also conducted with Ti64 alloy. It is gas turbine blade. As you can see in bottom right graphic, these parts have complex overhang inner and outer part. By combining Ded technology with simultaneous 5-axis control, complex shapes like these parts can be manufactured. Now, I will talk about manufacturing perspective. The fourth value is large scale. Ded can be worked in a way that continues to grow in size without being affected by the stacked environment. Recently, some projects try to use multiple lower arms to manufacture single parts. InssTek also interested in this project, internally researching multiple lower arm system for multi-material manufacturing. The project name is NARE. In our project, 4 robot arms are independently controlled. The maximum printing volume is 3.5 meter diameter and 7.5 meter height. With this volume, almost every part in aerospace can be printed. Pictures on the right side are repair examples of aerospace industry conducted by InssTek. With Ded Technology, repairing worn parts such as compressor blade and jet engine air seal are available. Now I will conclude this presentation with summaries. Materials used in extreme environments are difficult to manufacture with existing metal manufacturing processes, and there will be many new alloys to be studied according to the field's requirement. In the future, the world will need new alloys and new combination of materials to overcome the extreme environment. Thus, we think multi-material manufacturing will be the important keyword. For successful multi-material manufacturing, material research and industrial applications must be closer and move as one process. InssTek works for expanding multi-material manufacturing, so we made a machine for material research MX Lab and industrial machine MX Fab and MX Med. For this wonderful process, first step is material research using DED. Researchers try to make materials with suitable properties for industrial applications. DED is the only method to material research with changing the alloy composition. InssTek wants to pioneer this field with research experts here. Finally, I will end the presentation by showing a brief teaser video. This teaser video is the future plan of the InssTek. InssTek wants to stably manufacture such super large output based on material research.